Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I would like to thank all of you for joining me today in our webinar. Today, I'm going to be giving you all some excellent AFT software troubleshooting tips. These are things that all of us applications engineers here at AFT typically will employ when we are troubleshooting model files. And a lot of times, will be sent model files where the support ticket literally says model won't converge, please help. So I'm going to give you a lot of good pointers today on things that we look at and things that we look for when we start going through and diagnosing a model. And before we start looking at the details of things, it really all comes down to model input. That really is the biggest cause of model convergence or warnings or issues that you might see. Rarely is it ever related to your tolerances. That's one of the first things that people will typically jump to is adjusting the tolerances. If their model is having troubles converging, do not do that. That is not the best first step to approach. Chances are when you're having troubles getting a model to converge, it's because of other things, not the tolerances that you are using. So that's the key thing, is it really all comes down to model input. All right, let's go ahead and get into this. The webinar is being recorded as usual, and a link to the recorded webinar will be sent out to each of you listening in live. That way you could listen in again later if you like, or you can feel free to send the webinar around to your colleagues. I did include a copy of my presentation for those of you who are listening in live. There's just a few slides. I'll be showing most of the information in the software today. And if you're listening to the recorded version, feel free to email me at benkeyser@aft.com, and I'll be happy to send you a copy of my presentation. That's benkeiser@aft.com. All right, so just really quick, the first slide that you would see will provide you direct links to each of our web pages that talks about that specific product. So if you want to learn more about AFT Fathom or Impulse or Arrow, or perhaps any of the add-on modules, which are incredibly useful tools that will enhance your flow modeling capabilities, you can just click on any of those links and it'll take you right to that particular page on our website. So be sure to check that out when you get the chance. All right, so I'm gonna do a dump of all of the items first to show you what I look for when I'm troubleshooting a model, and then I'm going to go through a few examples in the software itself. That way you can see what it would actually look like. So the first thing that I do when I start looking at a model file is I'm going to create my own troubleshooting scenario. I'm never going to do any work looking at the main scenario that has the problem. I'm always going to create a child scenario of that, and after I create that child scenario, I can change whatever I want in the child scenario, and then I can always go back and reload the original scenario and preserve the original issue as it was in its original state. So you're going to see what that looks like today. So whenever you're doing your troubleshooting, do it in a child scenario, not the main scenario that you're actually having the problem in. Now, there was one thing that I just thought of that I actually totally forgot to add to this list, and I'm just going to go ahead and put it in there right now. We're going to call it check maintenance release. That's a really important one. I would say 7 or 8 times out of 10, whenever someone has a issue with the software, they're using a really, really old release of the software. And simply updating to the latest maintenance release will typically solve just about any problem that you're having. So That's another important step to complete when you're troubleshooting a model is check to see what maintenance release you're using. Go to our website to see if we have a maintenance release that is newer that you can download, and then go from there. So those are the first two things. I would probably even put check maintenance release first. That's the very first thing I do is I look at your model file to see what release that you're using. And a lot of times I find people that will send me models where they're using a maintenance release or even a version that's 3 years old. No wonder there's issues. So, when we're enhancing things and adding in new features and new capabilities, that's going to help a lot of those issues that you might see go away really quickly. All right, so again, I talked about solution control. The default tolerances that we provide will solve about 98% of the cases for you, so rarely will you ever need to go into solution control. That's the third thing that I check once I get into the model is the solution control that the user was working with. And if I see that they're not using default solution control, that's the very first thing I change is I set it back to the default AFT Fathom or AFT Arrow or Impulse solution control parameters because that's the best that is going to solve the majority of the cases that you'd be working on. Next thing I take a look at is the system properties and fluid phase. It's just good to know what type of fluid that you're working with. Are you using the ChemPack database or RefProp? Are you dealing with mixtures in your model? Are you working with non-Newtonian fluids? What kind of fluid properties are you modeling? It's just good to get an idea of what's going on there. That way it can help, if I see that, heat transfer or non-Newtonian fluids, that's going to add multiple layers of additional complexity to the model, and that's really helpful to be aware of. Next thing I take a look at is the model data window. I look for units that are inconsistent with each other. Maybe all your pipe lengths are in feet and one of them is accidentally in micro inches. I don't know how that would be the case, but that's one of the things that I look for is unit inconsistencies. The model data makes it really easy to be able to spot those types of mistakes. You can also find typos, incorrect data, and so you're going to see the model data window a lot today when I go through my troubleshooting techniques. Another thing I look for is detailed T's. It's important to account for losses through a T in your flow model, and AFT software uses idle check T's relationships for quantifying those losses, and they're based upon your flow distribution through the T as well as the area ratios, and they're very complicated relationships. And a lot of times what we find is when people define their T's, they don't get the orientations correct. And so if you define your orientations incorrectly, A, it's going to lead to incorrect results. B, it very well could cause convergence issues. And so typically in systems, the amount of frictional losses that your T's will add to your system are usually negligible in comparison to your other heavy loss components in the system, such as valves, orifice plates, long runs of pipe, heat exchangers, things like that. So a lot of times you can get away with using simple T's and your model will still carry on a very high level of accuracy. And so that's one of the things that I look for. If the model is not converging or if it's having an issue and I see that detailed T's are used, that's one of the other first few things that I'm going to change is to help simplify the model to diagnose what the problem is. Another thing that I look for is bad resistance curves and bad pump curves. Let's talk about this for a second. Let's say that you have a pump curve and you are using a polynomial curve fit to fit your data points. Well, sometimes there might be a little bit of scatter in the data and you might be tempted to use a third or a fourth order polynomial curve fit to help get a better fit of your data. That is okay, but when you're using a third or a fourth order polynomial curve fit, it could create some problems. One of those problems that you might see is where your pump curve might have an inflection point. So the thing to check when you're entering in your pump curve and you're fitting the data with that curve, make sure that your pump curve crosses the x-axis. If it does not cross the x-axis, then you might want to use a second order curve fit or an interpolated XY curve fit. So always check to make sure that your pump curves are going through the x-axis and they don't have this inflection point behavior. As far as resistance curves go, those can be just as problematic. When you're trying to quantify a loss across a component, it's really helpful to specify data for your pressure loss as a function of flow rate. Oftentimes, people might only know a single data point. So at a certain flow rate, they know that they're going to have a certain amount of pressure loss. So if you were to specify a single data point for a resistance curve, it's going to create a horizontal resistance curve that is just incorrect. This represents the same amount of frictional resistance across all flow rates. That's just completely wrong. And then also the reason why this could be an issue is if your system flow is actually really low, this would represent essentially an infinite resistance, and it very well could cause convergence issues. So if you don't have any other information other than a single data point, you can use the feature what's called Phil's quadratic, and that'll generate a much more accurate resistance curve for you. That's a better curve fit, and I'll show you what that looks like here in one of the models that we'll be diagnosing today. Other things I take a look at is your boundary conditions. What are your boundary supply pressures or your discharge pressures? If you're using reservoir junctions or tanks to model boundary conditions in your system, what are the liquid surface elevations? Where's your pipe depth or your elevation? What type of units are you using? If you're doing heat transfer, what are your temperatures? What's the fluid phase? If you're doing heat transfer, or if you're using AFT arrow and you specify a certain liquid level or a pressure, as well as a corresponding temperature, does that pressure and temperature result in saturated conditions? If it does, then that very well could cause convergence problems because the software is designed for modeling single-phase flow, not two-phase flow with saturation conditions. So boundary conditions are really helpful to make sure that those values are correct. A lot of times I'll see people that have specified initial guesses. You do have the ability to enter your own initial guesses for pressures and flow rates into the model, and that's perfectly fine, but I have seen a lot of cases where initial guesses cause convergence difficulties, and it can send a solver off in the wrong direction potentially. And a common troubleshooting technique is to simply clear out all the initial guesses, and that will help solve the model. So sometimes you might need to remove them. Sometimes you might need to add them in. If you don't have any initial guesses and you have a lot of model complexity, maybe you do need to specify some initial values for pressures and flow rates. You might have to do that from time to time. The key thing is, though, most of the time, the AFT software has its own ability to create its own initial guesses for you, where it doesn't need you to do it for it. So a lot of times, just let the software do it itself, and it'll be fine. Other things I take a look at is heat transfer. One time, I had somebody send in a model file that had, a couple thousand pipes and junctions, and they had 300 heat exchangers in their model. And in their model, I saw that they were using heat transfer as I was going through and doing my regular model diagnosing process. And I looked at their heat exchangers in the model data window, and I saw that all of their heat exchangers were specifying a controlled outlet temperature of 321 degrees Fahrenheit. Okay, well, that's fine. I mean, depending on the fluid and the pressures that you're operating at, this very well could be a liquid, and that would be a perfectly fine temperature to use. However, in 5 of the heat exchangers that they used, they were not specifying a specific temperature. They were specifying a delta T of 321 degrees Fahrenheit. So these are very, very different values, and this is what was causing the model to not converge. It was another one of those cases where they sent me a model file and said, model won't converge, please help. Well, with using the model data window to check for units and typos for heat transfer, I was able to quickly spot those 5 heat exchangers that were the problem. I quickly changed them to use the same temperature and condition as the other heat exchangers. Model was able to converge like a charm. So again, don't underestimate the power of the model data window, and it's also really helpful when you're looking at heat transfer, because there might be some weird heat transfer input that might have been accidentally specified. Another thing I check for is reference pressure issues. Well, this is not really something I check for. It's more something that users will typically run into. Essentially, if you have a fixed flow at one point in your model and another point in your model in series where there's another fixed flow rate, it's possible to calculate a dP that will drive that flow. But what's the pressure at the inlet of this pipe, or the outlet of this pipe, or the middle of this pipe? It's unknown. The reason why is because there are multiple solutions for pressure that exist that will give you the required dP to drive that flow. So the reference pressure is something that you'll see quite often when you have fixed flow rates in series with each other, and the model won't even run because you have to have a unique pressure specified somewhere in that flow path. I'm going to show you a couple of examples of where you can find some help topics and a walkthrough tutorial that will teach you how to get around that type of issue when you see it. All right, let's see here. What else we got? Warning messages. A lot of times we'll be able to provide warning messages to the user telling you that there's various issues in the model. The key thing is read the warning messages. Don't just ignore them. Read the warning messages and understand what they say. Also, if you read a particular warning message and you're not entirely sure what it means, you can click on that particular message, hit the F1 button on your keyboard, and that will bring up the help file where you can read more information about what that warning message means. I'll show you that in a little bit here as well. So be sure to not just ignore your warning messages. Control valve failure is another common issue where we have a input specification in the control valve window that is turned on by default to always control, never fail for your control valves. The way that a control valve will work in the software is the software is going to modulate the pressure drop across the control valve to meet your set point. Once your set point is met, the pressure drop is known, the flow rate is known, therefore a CV value can be calculated. And we know all the conditions through the control valve in that case. However, if there's a time where your flow control valve fails, there's an option where you can always control, never fail, no matter what. What that will do is if your pressure drop across the control valve hits 0, there's no more pressure drop that can be taken out across your control valve to hit your set point. So what the software would then do is it will add more pressure where your control valve would start acting like a pump in order to meet your set point. Well, that is obviously physically unrealistic, but it's really useful for troubleshooting purposes because it will give you a good indication as to which control valves will be able to control and which ones can't. So if you have a control valve that is only having to add 2 pounds of pressure, you would see negative 2 psid perhaps. This is a lot more close to controlling than a control valve that's having to add 50 pounds of pressure. So this might give you an indication as to what's happening in your model that's causing your control valves to fail. Maybe there's an internal bottleneck or something somewhere. Maybe there's an incorrect diameter in one of those pipes. So that's really helpful feature to leave on. And that way you'll be able to troubleshoot a little bit easier. All right. Let's see here. What else we got? ATKF correction. So I'll talk about this in a little bit here where the software can add correction factors to your minor losses for fittings if they are operating at laminar or non-Newtonian flow conditions. The reason why this is really important to add in correction factors is because the K-factor loss models that are standard developed by Crane, Idlecheck, and Miller and whatnot, those were developed under turbulent Newtonian flow conditions, and the loss models may not directly apply to laminar flows or non-Newtonian fluids. And in those types of cases, typically the standard loss models will underpredict the pressure losses when you have those circumstances. So the correction factors will be able to add to that. So when you're running your model, if you see weird results, check your Reynolds numbers, because the software is going to add those correction factors for you by default if you have laminar flow or non-Newtonian fluid properties. That way, it'll give you the actual pressure losses across those types of fittings. Something that you also might need to do once in a while is massage your model towards convergence. Maybe you're trying to get convergence based upon a really high supply pressure, and for whatever reason, initially, your model won't converge with the high supply pressure. One thing that you can do is start with the lower pressure, run your model and get convergence, transfer your results to initial guesses, and then slowly increase your supply pressure one iteration at a time. Another point where this is helpful is if you have a very complex model with lots of branching or lots of looping. With all those branches and loops, it could get difficult for the model to be able to solve, especially if your flow distributions are very similar. So a technique is to shut off several flow paths and just have a single flow path turned on, run your model, get convergence, transfer results to initial guesses, and then turn on other additional flow paths, and that way you'll be able to get convergence over a series of iterations. Cavitation could be present in your system. AFT Fathom will identify where cavitation is happening in your model, and that way it'll check the static pressure with the vapor pressure, and that would tell you where you have a problem, but it does not model the actual cavitation itself. So that's something that you would need to use AFT Impulse for. Similar thing would be saturation conditions in AFT Aero. If you're modeling a gas and you are using either the Chempact database or ASME steam tables or RefProp, you might tend to have saturation in your model. That's where your results would be uncertain. So where it pinpoints where the saturation would be occurring is a good place to go and review your model to see where you might have a problem. A few other things, you can sort output data. So, an example is maybe sorting velocities in increasing order, or maybe sorting your pressures. If you have a lot of pipes in your model and you sort your velocity for each of the pipes, that can make it really easy to find really high velocities where an incorrect diameter might have been used. Closing off parts of the model is another technique, and so this is a really good list of things for you to look at. So again, the PDF is available to you for those that are listening in on live. If you're listening to the recording, email me and I'll send you the presentation. And this way, when you're going back and you're starting to have model issues, or if you're checking somebody else's model, these are some really good places to start, and that can help you quickly find the problem. All right, let's take a look at some examples now. So the example that I want to do first is this particular model file that does not have convergence. And so I'm going to go ahead and move my PowerPoint presentation to the side, and then I'm going to open up that model file, and we're going to run it and see what happens. And as I go through the model, I'm going to go ahead and do a detailed check of each of these parameters. And I'm really tempted to jump straight to the answer, because there's two things that are preventing convergence and correct issues, or correct answers with this particular model. But I'm going to go through all of these steps as well to show you the things that I look at. All right, let me go ahead and open up the model. Give me one quick moment here. Okay, so the user sends me this model and says, AFT, could you please assist? The model does not converge. Well, what do we do first? The very first thing, I'm actually going to switch these two. Check the maintenance release first. That should be the very first thing that you always do, is check the maintenance release. How do you do that? Well, if you go to the help menu, and then you come down to AFT Fathom, or correspondingly AFT Arrow or AFT Impulse, this window here gives you a lot of information. It tells you the version number that you're using, as well as the release date for when that when the maintenance release came out. And it also displays your license number as well. So if you ever need tech support and you're not sure what your license number is, just open up the About, and this is where you can find your license number. All right, so once I go in here and I check the maintenance release, I see that I'm using the maintenance release from October 20th, I'm using the maintenance release from October 3rd, 2019. Well, what can I do next? After that, I click OK, and I can go back to the help menu. And what you can do is click on this option right here, Internet Latest Release. So here's where you would be able to download the latest release of AFT Fathom. All of them are available in the Downloads menu, and this is the current maintenance release that's available. So I am using the October 3rd of 2019 maintenance release. Compare this date on our website with the date that you are using, which again, help AFT Fathom. As you can see, these two dates correspond with each other. I'm using the latest maintenance release. We're good. So that's the first thing that you do. If you're using one that's older right here, then you need to update to the latest release. Everyone should have the ability to at least download the latest maintenance release. You may not have the ability to install it, however. So if you go to our website under downloads and then current versions, and then pick the AFT product that you're working on, the first thing that you're going to see is this message right here. You must be logged in to download software. Well, here's the thing. Anyone can download software from our website. We do not restrict it to anybody. All you need to do is click on the login button and create an account. It's really simple. It's really easy. Anyone can do this. It's not restricted in any way whatsoever. You would just click on the button that says register. And then once you click on register, simply fill out the form of this information. And once you fill out that form, you'll be sent an email really quickly with an activation link that will then allow you to be able to log in with your email address and your new password. Now, if you do not see that email really quickly, right away, then be sure to check your spam or your junk folders, because a lot of times the activation link will end up in your spam or junk folders. If you don't see it in your spam or junk folder, contact AFT and we'll be able to help you activate your registration. So once you get registered, you would type in your email and your password to get logged in. Now, when you go back to download the latest release, this is where you can download it from. So everyone should have the ability to at least download the latest maintenance release, but you may not have the administrative privileges to install it. So then you go and bug your IT department to have them download or install the latest release for you. It's critical to make sure you're using the latest release so that you have all the appropriate fixes that you need that might resolve whatever issue you're running into. We also will show you the release notes for that particular version. This documents all the changes that we've made in each maintenance release during the lifetime of a particular version. This maintenance release, or the release notes, it's also installed with the software as well. So if you were to browse where AFT Fathom is installed on your computer, it's in a readme.txt file right here. This is your release notes that comes with the software installation. And that's always going to have the latest. So be sure to keep an eye on those maintenance release notes, and that'll tell you exactly what we changed from release to release. This is an important field to fill out. That way you can be sure to receive notification emails whenever we put out a new maintenance release. It will contain a download link where you can get that download from our website. In addition, you can go to the support and then manage notifications, and this is where you can subscribe to receive notifications for all of our maintenance releases for Fathom, Arrow, and Impulse. Our newsletter contains a lot of useful information such as product updates, new AFT products that are available, tips and tricks articles, video tutorials, lots of stuff like that. Okay, back to the software. Okay, so first thing is completed. I have checked the maintenance release. I'm using the latest release, so I'm going to go on to the next one. I'm going to create a troubleshooting scenario. So this is the scenario right here that is the problem. So I'm not going to do any mucking around in this scenario because I want to preserve how it came to me exactly as it was. So what I'm going to do is I'm going to click on this button to create a child scenario. So I'm going to create a new scenario called AFT. You can call it whatever you want. This way, you can go in, you can change whatever you want to change in the model, and then later on, if you decide, hey, any of those changes I made, I don't like that scenario anymore, I want to delete it, well, you can. So after you make all those changes, if you don't want to keep those changes, you can right click and delete the scenario and then simply create a new one. AFT round 2. And so now this is the scenario where you're going to be mucking around with. And if you want to document the changes, as I mentioned, this is a whole big list of different things that you might look at. And if you want to document your process as you go along and you're looking at those different things, you can type in notes for that particular scenario. That way, when you're doing your troubleshooting, you can document every step that you've taken in order to get a model to converge. Because there might be a number of things. Maybe you need to adjust solution control, detailed T's and resistance curves, or different things like that. If you're tracking every step of the way that you're going, it'll make it a lot easier to remember what you did to actually get the model to work. All right, so that's my first two things that I've wanted to look at. The next thing is to check the solution control. So where do you find solution control? It's in the analysis menu. So if you go to the analysis menu and click on that drop down, I'm going to open up the solution control, and just because I've been doing this for 8 years, I know exactly what the default tolerances are. The default tolerances are to use relative tolerances for pressure and flow, and the tolerance value is 0.0001. That's 0.01%. And then also, I know exactly what the tolerance default values are on the general tab and special controls. So the first thing I look at in this model is solution control. Sometimes I might see something like this, where people have loosened the tolerances. This is very, very bad. This may give you convergence, but it will not lead to correct answers because that may not be a very tight enough convergence. So the very first thing I'm going to do is I'm going to come into the solution control window, click on Fathom Default, and click OK, and I'm going to be off to my next step. So that's the third thing that I do is I just set the solution control to the default parameters. Next thing is let's look at system properties. System properties is also going to tell you if the user is working with heat transfer, and I'll also show you where you can find information about the ATKF corrections, and we'll talk briefly about cavitation. All right, so the next thing I'm going to do is click on System Properties, which is the pink flask right here in the main toolbar. And again, I'm just going to go through, I just want to see what's being modeled here. Well, this is really simple, but I'm using the AFT standard fluids, so that's a really simplified thermodynamic model. Water at 1 atmosphere is being used at a temperature of 70 degrees Fahrenheit. Here's all my properties, and I'm using constant fluid properties. If somebody was using heat transfer, one of these two options would be checked. If either of those two options are being checked, then that's going to tell me that there would be some potential heat transfer input that I need to check because maybe the heat transfer is causing convergence issues. Maybe it's not. But if you look at your system properties window first, it'll tell you if you even need to look at heat transfer. So because the particular model that I'm working on is not doing heat transfer, that's a whole step that I don't have to go through and look at anymore. The other 3 fluid modeling options for ASME steam, tables, or RefProp from the National Institute of Standards and Technology and ChemPack, those are all using very, very sophisticated thermodynamic models for calculating the thermodynamic thermophysical properties. So if any of those options are being used, this is adding another layer of complexity to the model, especially if you're working with RefProp or ChemPack and you're using mixtures in your model. So if these options are being employed, that's just good to know as you're troubleshooting your model that that's potentially adding another layer of complexity that you might have to dig into deeper later on. So if you are using either of those two options and you're having troubles, what you might want to try as a troubleshooting step is simply try AFT standard. And if you're using AFT standard, these are more simplified models. This might be able to give you convergence where one of these may not. Well, why would those options not give you convergence? Maybe you're saturated. So if you're saturated, then that could be why those 3 options would potentially give you difficulties in converging. So that's one troubleshooting technique. Another troubleshooting technique is if you're using heat transfer and you're having troubles getting convergence, again, just do one of your troubleshooting steps in your child's scenario where you set it back to constant fluid properties. That eliminates all that complexity where you can just focus on hydraulics. Those are all things that will help pinpoint what the issue might be that's causing the model to not converge. All right, let's take a look at the viscosity model. The viscosity model here is Newtonian. We do have additional non-Newtonian options that you can work with. And then on the system data tab, this is where you can turn on correction factors for ATKF. Really, if you're operating with laminar flows or if your fluids are non-Newtonian, there's actually multiple industry methods for adding correction factors. There's a 2K method, a 3K method, there's equivalent length methods, adjusted turbulent K factor methods. Basically, Fathom and Impulse has all of those methods built in, except for the 2K method. That one is not the most accurate. But this is one of the areas where you can turn on the adjusted turbulent K factor method. Click on the question mark. When you click on the question mark, this is going to bring up our help file that will talk about what that correction method is. You can then go to this link right here and you can read more information about it. So if you go to that option right here, you can read all the details behind what the ATKF method is. And then if you click on the improved method, this will talk about what that is. If I go back a couple of help topics, this is a really good technical paper that you can find on our website. This is an article where the adjusted turbulent K factor method was able to help solve major operational problems that DuPont was having. And the reason for the issues is their original flow model, they were neglecting the correction factors, and once they added on the correction factors, they were able to know exactly what the conditions would be, and that's how they were able to solve their problems with the non-Newtonian flows. So read that technical paper, and it'll give you a really good study as to when you would need to use those correction factors. So just know, even if you're doing a Newtonian fluid model, if you see very high K factors or really high pressure losses across your fittings, check your Reynolds numbers. If your Reynolds numbers are in the laminar regime, then there's a good chance that we're going to be applying those correction factors. All right, so those are the things that I look at in the fluid or in the system properties window. All right, now before I go on to the next steps, let's just go ahead and run the model and see what's happening. Again, the model came to me in this particular state. When I click on run, the user said the model just takes forever to solve and it never gets to an answer. Well, we could sit here for an hour or two and wait for the model to converge, but it may not ever converge. So to prevent that, in the solution control window on the general tab, we have this limit right here for maximum iterations. Most models will easily converge within about 10,000 iterations, usually a lot less. However, it might be required where a model would require 100,000 iterations. Well, this value does not affect the results at all. It just sets in a limit so that you're not sitting there for hours and hours and hours or for an eternity with a model that will never ever converge. So after 50,000 iterations, if it can't solve, it's going to just stop solving, and it'll tell you it won't be able to converge within 50,000 iterations. Once in a very blue moon, you might need to up that to maybe 100,000 iterations. But again, that's extremely rare. So whenever you're encountering convergence issues, even in this particular model itself, where the solver just keeps running and running and running and running and running and never getting anywhere, it's not solution control that's a problem. It's usually something else. So let's keep diagnosing the model and let's see what's going on here. What's my next step? Well, let's look at the model data window. Let's see if there's any inconsistencies in data. So the model data window, this contains a tabular format for all of your input information. And so this is a really good place to turn to. I'm going to collapse my quick access panel, so I have a little bit more space there. The general section gives you basic information about your model. If you are entering in any information on the notes tabs for your pipes or junctions, or if you have any scenario notes down below, any of those notes that you've typed in are going to be cataloged in the notes tab here in the general section. The piping section contains all of your input information for your pipes. If you have fittings and losses, there's a detailed pipe summary, and then we have our junction information. So again, when I'm going through and I'm troubleshooting a model, I look at things bits and pieces at a time. So I'm going to start with looking at the pipes tab, and I'm just scanning down this column of data, and I'm looking for unit consistency. You know, a lot of times people might use both feet and millimeters in a model. That's perfectly fine. Fathom can handle feet and millimeters all together in the same model at the same time, no problem. But the issue is it just introduces more chances for error and more opportunities to have typos. So keep your units consistent, and that will help ensure that you have the right results. But maybe this is not millimeters, maybe this is inches. Well, again, just make sure that your values are correct. And if you're using multiple unit sets, that could be a source of error. So that's one of the first things I check is unit consistency. I also look for orders of magnitude. You know, maybe somebody had, accidentally typed in a few extra zeros. Well, this is going to be very, very obvious to you if you're using the model data window to find those inconsistencies where things are off by huge orders of magnitude. So that's another thing that you can check is orders of magnitude. In this pipe right here, if I have fittings and losses, let's put a K factor there. That's where we will now see a K factor on the fittings and losses tab. And this tab here will tell you that you've got losses in that particular pipe. If we go back to the workspace, this red ampersand means that you have fittings and losses on that pipe right here. That's all of that means. It's a visual indicator that tells you you've got fittings and losses there. And so I just wanted to do that really quick to highlight what this tab does. It's going to catalog a summary of all of the fittings that you've lumped in to each of the pipes throughout your model. Now I'm going to go in here and I'm going to delete this because that's not part of the model. All right, so we can scroll over, we can check our diameters. We've got some 3-inch and 5-inch diameter pipes. Okay, I don't see really any issues. Now, I'm not showing every possible piping parameter in this table right now. That's where you would use the model data control. So if you open up the model data control, this is where you can dictate which specific parameters for pipes and parameters for junctions are being shown. So if you want to turn on additional parameters for your pipes, well, there are 47 total parameters that you can include. I'm only looking at 13, but hey, let's go nuts. Let's look at all of them. So here, you might be doing this just to go through. Another thing to check for is design factors. Look for design factors. If you see design factors in here, this could be a reason why your results may not be what you're expecting, is because if you specify design factors, it's going to slightly modify your output results based upon those factors that you're including. So when you add the design factors into your window here, it makes it a lot clearer to see where those might have been specified. And we can just keep going to the right, and we can keep seeing any information that we might have specified. Here's where we would find fluid and heat transfer information if we were modeling heat transfer in our model, so on and so forth. So that's all of the piping parameters that I'm showing in this list. The next thing, let's look at our junctions. The junctions are just as important to review the input for. So one of the things I look at is boundary conditions. Well, this particular boundary here is an assigned pressure, and it's assigned a supply pressure of 20 psi-A. Well, that's perfectly fine, but if this is supposed to be psi-G, you'd want to pay attention to those units. So that's my supply pressure boundary. My reservoir here contains my liquid surface elevation as well as the liquid surface pressure. This is where pipe depth or pipe elevation is important, especially if you have multiple pipes connected to a single reservoir junction. I've seen cases where people have specified a liquid surface elevation of 30 feet, but maybe their pipe elevation is 45 feet. Well, what this means is that you have a reservoir with some liquid level. The pump or the pipe is actually going to be dumping in above that liquid surface level. So if you're discharging fluid into the reservoir, that's okay, no problem at all there. However, if your atmospheric pressure at the inlet of this pipe or whatever your surface pressure is in that tab is larger than the pressure in your piping, you're going to potentially have reverse flow. Well, if your pipe is above the liquid surface level and you have reverse flow, you're going to be sucking in air, not liquid. And you will see a warning message that tells you that. So this is just another thing to look out for, is when you are connecting your pipes to your reservoirs, be sure to check the pipe depth or the elevation levels to ensure that they make sense and that they're correct. All right, so those are my boundary conditions. So that's another thing that I can cross off the list here. So that's done, that's done. Let's take a look at the other information for junctions. So just keep going through one at a time. Another thing that I look at is elevation information. I want to see if my elevations are consistent. If I have 0 feet for all of my junctions and 180 for one of them, that's going to tell me that something is not right. So I'm going through, I'm checking all of my junctions for relatively consistent orders of magnitude on their elevation values. I'm looking at the data here, so on and so forth, and there we go. So I'm just getting a feel for what's going on in the model. Now, as I mentioned, detailed T's are one of the most common sources of issue. Well, the model data window makes it very clear where those detailed T's are specified. So if I go back into my model data window, I can see that both of my T's are detailed. Now, let's talk about this for a quick second. Let me erase my drawing. You can take this T and you can rotate it all around all day long. That's not going to have any impact on the results whatsoever. However, the orientation inside the property window right here, this is what makes a difference for detailed T's. So if you're going to specify detailed T's, you have to make sure that all of this information is exactly correct in accordance with your drawings and your actual flow distribution. One time I saw a model file that had a whole bunch of detailed T's, and in their drawings, they had something like this where they had a heat exchanger here and a heat exchanger here, and here was where their T was, and this would be the branch pipe according to the as-built drawing. In the model, they modeled it like this, where they put the heat exchanger there and another heat exchanger there, and as you can see by the way that they drew the model, this was their branch pipe. Well, those two are not the same. So this will lead to incorrect results, and it very well could lead to convergence issues when they're not oriented properly. Now, I don't want to spend too much more time on detailed T's themselves. We have some blog articles on our website that you can find about tees. And so if you just go into our tips and tricks page and do a keyword search for detailed tees, you can find some really good articles about detailed tees. And this will go into detail about the really complicated relationships that we're using. So you have to make sure that you get those orientations correct. So in my model here, I'm going to set these to simple. I'm going to see if this gets my model to converge. So I'm going to go to edit and then global junction edit, and I'm going to change both T's to simple. So I'm going to click on all, and I'm going to globally change them both to simple T's. Simple is already checked off, so I click OK. The only change I'm making is to change them to simple T's. I don't have to check any other boxes. And then I click on Apply Selections, click OK. So now if I go back, I can see that I'm using simple T's. Let's rerun our model and see if we get convergence now. Well, we do. This is good. We are another step further in our analysis. Our calculations have completed, but look at this. Rerunning solver because one or more junction states have changed. Well, that's telling you that there is some junction in your model. Maybe it's a control valve, maybe it's a check valve, or it might be a relief valve. If any of those special types of junctions that can change a state during the solver, this message is going to give you an indicator of what happened. So once it gives you an indicator that happened, we click on the output window, and what we can see here is that the flow control valve could not control the flow at junction 4. So here's junction 4. There's our control valve. And if I open this up, I told you how initially this is usually checked by default. In this case, it was unchecked. So our flow set point is 100 gallons per minute. That's what we're trying to achieve through that control valve. Well, Fathom is trying to decrease the pressure loss across that control valve in order to get its set point, and it gets to a point where it cannot remove any more pressure, so it's at a DP of 0. That control valve is going to fail right open, and when that control valve fails open, it's going to give you the maximum amount of flow that it can possibly give you. Now this is really weird. The control valve is failed open, but you're not even getting a single gallon per minute of flow through that control valve. What in the world is going on here? As a FYI, let me go back to the warnings tab really quick here. I mentioned read the warning messages. They will tell you what's going on. And if you're not sure what that message means, follow this suggestion. By selecting a warning message, hit the F1 button on your keyboard. This will bring up our help file where it documents all the various warning messages that you might see. You can then go in and click on any of those particular warning messages, and that way you'll be able to read a description of what it means. So when it says control valve failed right here, this will tell you what it means. Now, obviously, this is a very, very short topic. Doesn't give you very much information, but read the related topic, control valve failure. That's because there are some different nuances on how control valves will fail in your flow analysis. So this is really important to read. Okay, so what is causing this control valve to fail? Well, it's difficult to pinpoint simply by looking at the results, but if you do want to sort the data like I was talking about, you can simply right-click on any of these columns, and you can say sort in ascending or descending order. So you can do that for velocity, or you can sort by descending order for inlet pressure. This might be able to help you pinpoint where you might have some particular issues. Well, let's go back to our model data window. Let's take a deeper look at the model data for the input on each of our junctions. So here, if I look at my pump, if I have multiple pumps in parallel, I want to make sure that they all have the same constants. If they all have this, if they have different constants and I have pumps in parallel, well, that could be a potential issue, because when you're pumping pumps in parallel, you want to ensure that they have the same pump curve as much as possible. So if you have pumps in parallel and you're seeing different constants for each of them, then that's not a good thing, and your pump curves may not be the same. Now, Fathom could model, dissimilar pumps in parallel. No problem at all. It's just going to mathematically figure out where each of the individual pumps are operating, but it could be a source of input error that you would want to know about. How do you check to make sure that your pump curve is crossing the x-axis? Well, if this was at a lower value, let's call it 300, this is as far out as my graph goes. So if I extend the maximum x-axis value out to a larger number, then that's where I can clearly see that the x-axis is crossed by the pump curve. So it crosses at a DH of 0. This is what you want to be able to see. If you were using a third or fourth order polynomial and you might have an inflection point, that's where this would be very, very clear. How do you model a third or fourth order polynomial? Well, when you go to enter your curve data, you would just choose polynomial as your curve fit, and then your curve fit order right there, and that's where you can do a third or fourth order polynomial curve fit if you want. Note, we are not ever using the actual data points for your calculations. So whenever you are entering data, we're not using that actual value for calculations. We're fitting it with a curve instead. So make sure that your data points lie on that curve fit decently well, and that will help you achieve more accuracy. Okay, so my pump curve is fine. Let's take a look at the general components. These three general components represent some sort of, maybe it's a process unit, and there's going to be some sort of frictional loss across it. Well, this is one of the other things that I go through and I check. I talked about pump curves. Now I'm going to look for bad resistance curves. So when I go in here to look at the model data window, I'm going to go to general component and then I'll scroll over, and would you look at this? I have three general components in what seems to be the same area of the model, and they have different constants. These two are the same. This one is completely different. Well, what in the world is going on there? Let's take a look at these. If I double click on this, I can open up my enter curve data window. You want to ensure that you at least have a data point through the origin. You should always include that 0, 0 data point. Now, if you only have a single data point, let's say that our specification only tells us that at 200 gallons per minute, I have a 2 psi pressure loss. This is a spec sheet pressure loss data point. I don't know any other information. If you were to try and generate a curve fit and you're using one of the latest versions of our software, it's going to try to prevent you from generating a bad resistance curve. But if I want to do it the wrong way anyway, that's the horizontal resistance curve that I was talking about. That's going to give you potential issues, and it's just completely wrong. However, that's not the issue in this particular model. But what you could do is click on fill as quadratic, and bam, that's going to generate the 2 additional data points for you. That way, when you go to generate your curve fit, this is going to give you a much more realistic loss across that component. So this is what the curve looks like for that junction for both of them that are alike, but the one that is different, whoa, that's really weird. As you can see, it's starting at a pressure of 80 psi at 0 flow, and then it decreases. That's just completely wrong. Well, what had happened was the data was accidentally entered in backwards and incorrectly. An additional value, instead of 8, it was 80. And then instead of going 0, 2, and then 8, it went 8, 20, and 0. So there was typos on these curves. Now, if this component is supposed to be exactly the same as the other two, there's a really easy way to get consistency without having to re-enter that data from scratch. Instead, what you would use is click on this option right here, copy data from Junction. So I'm going to click on copy data from Junction. I'm going to use Junction 5 as the reference. And so now when I reset that data, look at that. All the constants are the same. If I open up, the resistance curve now looks the same. And if I go to rerun my model, bam, that gives convergence. I don't have any control valve failures. Each control valve is maintaining its set point at 100 gallons per minute, and my pump is operating on its curve. Everything is hunky-dory. Now, still, you want to make sure that you review your output to make sure all of your results are correct, but those are the two things that eliminated the issues. The detailed T's are what was causing convergence difficulty. But the major problem was this resistance curve right here that was backwards. They compounded on each other. So now what we can try doing is let's try going back in to the detailed T's and let's see if we can reset these to detailed and see if it works. So again, be sure that you get that branch pipe correct. I'm pretending that the T's are supposed to be oriented as the model is drawn. So this is going to be my branch pipe right here. So I have pipe 9, and then this is going to be pipe 11. And we'll click OK. And then we'll try this T being detailed as well. So I got detailed. This will be pipe 12, and then 10 is the branch pipe. And we click OK. And look at that. We made them detailed T's again, and the model converged. So really, the major problem was the general component itself, not the detailed T's. Once you got the general component, it fixed it. But you can see how the combination of the detailed T complexities interfered with the bad resistance curve, and that can cause some significant problems there. Now, let's go back and let's take a look at the losses through that T. If you go to junctions for T's and Y's, it says see multiple losses for your K factor. Well, look at this. Here's your K factors for each leg. If I add on the pressure loss through the junction, we can see how much pressure is lost across the T. Let's see. Let's try this again. There we go. So look at this. Even though we've got detailed T's, the pressure losses across them are very small. So this is where you can maybe get away with being all right with simple T's. So we've talked about each of these options right here of things to look at when you're having issues. We looked at our boundary conditions. Initial guesses. Let's take a look at that really quick. Initial guesses, as I mentioned, can cause convergence issues. If I see initial guesses that are entered right here for initial pressure, that initial guess is typically specified in your optional window. Now, I don't have initial guesses for any of my junctions, but if I did, that's where I would see initial pressures for junctions, and then I would see initial flow rates for the pipes. So if I see initial guesses, that could be something that prevents convergence. So to clear those out, just go to Edit and then Clear Initial Guesses, and that will clear them out right away. And then try running your model and you might be able to get convergence. Now, if you have to massage your model to convergence, maybe I don't want to change each of my T's to detailed altogether. Maybe I might want to do one at a time to ensure that it works. So if this is a detailed T and this is a simple T, what I might try to do to simplify the model is use the simple one first, run the model, and get convergence. After I get convergence, if you want to transfer those results to initial guesses, you can click on that thumbtack right there. So this will transfer results to initial guesses. This will give the solver a much better starting point the next time that you run the model. Now, I would go in and change this T to detailed as well. And then once I change that to detailed, rerun the model. The initial guesses can help it run a little bit faster. And this is one of the cases where you might need to do a little bit of model massaging, where you're slowly changing things bits and pieces at a time to get closer and closer to converging on an answer. So that might be one thing that you do is with T's. Another thing is by shutting off parts of your model. So maybe I might take these pipes and junctions and click on the red circle with the slash to it. That sets their special condition. So if you go to the optional tab for any pipe or junction, you're going to see a special condition of closed, and that way it closes off that flow path. So pretend that this is a really, really big, complicated model with thousands of pipes and junctions. If it won't converge in one shot with everything being turned on, try this. Select some pipes and junctions in a number of the other flow paths and turn them off. That way there's no flow in each of those paths. It makes the solver a lot easier to converge on one single flow path there. So now I'm going to rerun my model with one flow path turned on, transfer results to initial guesses, go back and I'll select the pipes and junctions in this area, turn on that path, rerun it. As I get new results, transfer the new results to initial guesses, and then go back in, select the next flow path, turn it back on, rerun it, and there we go. So this is really important of a concept, because if you have a really complicated system that looks like this, if your whole entire model is not going to run with everything turned on, well, try that same approach. In this particular case, this whole part of the system is turned off. So the only part of the system that has any flow is the pipes that are colored in black right here. So even though there's some parallel pumps and parallel general components here, it's still essentially a single flow path. So if you're not able to get this flow path to converge, maybe that means that the problem exists somewhere in this flow path. Now, if this single flow path converges no problem at all, maybe the problem is somewhere else in your system. So that's where using the model massaging technique to slowly get results by starting with a very simple state of your system, slowly making it more and more complicated and transferring the results to initial guesses in between, can do a lot better job at helping you get convergence. All right, one of the things that we need to talk about here, as far as the reference pressure message goes, I'm not going to go into detail about that. I want to show you some really important topics to fully understand in the help file. So if you go to the help file under contents and index, the very first section is called fundamental flow modeling concepts. Right here. These are all critical topics to read and fully understand to really help you be effective at flow modeling. It talks about static versus stagnation pressure, but the ones that are really helpful is how pressure junctions work, and then role of pressure junctions, and then you can read up on how AFT software handles open systems versus closed systems. If you click on the role of pressure junctions, this is going to highlight at a basic level what that reference pressure message is telling you, but I'm going to give you all a homework assignment. I want you all to read the detailed discussion, because there are several areas where this reference pressure message can pop up, not simply just using two fixed flow assigned flow junctions in series. It is possible where you could have different combinations of fixed flow values in combination with various pressure control valves, where you might run into a situation where you see that same reference pressure message. So be sure to read this article, and it will go into really good detail as to when that reference pressure message would show up, what it means, and how to get around it. So be sure to read that article there. All right, let's see what else we got. Talked about ATF corrections. As far as cavitation goes, just be sure that you have a vapor pressure specified in your system properties window. It's not a required input, but as long as you specify the vapor pressure, it will allow your MPSH-A to be calculated for pumps, but in addition, it will compare the static pressure in a pipe to the vapor pressure. And if your static pressure is lower than vapor pressure, that will be an indication you've got cavitation, and that's something that needs to be mitigated in your system. So be sure to enter your vapor pressures. All right. Now, I did have another example, but in this particular example, it's a lot more simplified, where I have 3 pumps operating in parallel, and then I have 2 identical flow paths. So I'm just going to go ahead and open this up really quick. Give me one quick moment. All right, so what do? First thing, check your maintenance release. Go to Internet latest release. Make sure you're using the latest one. You can see exactly which release you're using from the About menu. The next thing that you do is you would go in and create a scenario. I'll call this AFT. And the next thing I would do, the user says that the results are not matching what they expect. So what they're seeing is, if you look at the heat exchanger flow rates, I've got 82 gallons per minute through one of them, 440 through the other. Well, that's dramatically different. If all of this stuff is supposed to be the same, why am I getting very, very different flow rates in each of those 2 flow paths? Again, just keep going through my little checklist here. You know, we did the first 2 things already. Look at solution control. So I go in, analysis, solution control. I can see everything as default. If you don't have the default control memorized like I do, just click Fathom Default and click OK. And then rerun your model. Check the results on your heat exchangers. Same problem. Well, let's keep diving in. What fluid are we using? Well, it's just water, no heat transfer, nothing non-Newtonian, not too worried about ATF corrections, so that's probably not an issue. What are my T's looking like? Well, in this particular model, all of the T's are simple T's already. That's not an issue. Let's take a deeper look at the model data window. I've got unit consistencies for all my pipes. I have no issues of orders of magnitude. What you might want to do is carry your model data window off into a separate monitor, where you can go through and you can go in and look at pipe by pipe and look in that table to make sure that both paths are exactly the same. But if I start looking at my junction data, I've got my pumps. All of my pumps have the same constants. My reservoir, I'm checking the input for the reservoir. That looks fine. If I look at my valves, these are regular valves. Well, would you look at that? I have one of them that has a K factor of 624, and the other one is a K factor of 0.05. Well, that's what's causing the major difference. So here, this is showing me that I've got a K factor of 624, where it should not be that value. So you want to make sure that they're the same. So we got 624 and we got 0.05. So what I could do is in the one that's not the same, again, just go into J14, copy junction from the other data, but here I don't want to change the name, so I'm going to uncheck that box. And there we go. So now input is the same. I rerun my model. I get new results. I go back in, bam, same flow rates. There we go. We're all good. So if you were to apply this approach in this order, this is the order that I use. These are the things that I check off one at a time whenever I'm diagnosing a model. If you go through this order here, this will help you very quickly be able to pinpoint where the problems in your model might be, and you have a very good chance at figuring out what the issue is. However, your time is valuable. So now that you know this, give it the old college try. Try troubleshooting it yourself for 5 or 10 minutes. If you are still running into difficulties, send the model to us, support@aft.com. Let AFT troubleshoot it for you, because chances are, because we're looking at models all day long, every day, we are going to be able to find the issue a lot quicker, and we'll be able to find exactly what the issue is, rather than something that may or may not be the problem. So don't forget to take advantage of using technical support with AFT. Our engineers are outstanding and really helpful, and they're very quick to respond. They'll get you really good technical answers. And again, feel free to email support@aft.com. And as long as you're maintaining a current support upgrade and maintenance agreement, we'll be able to assist you. Well, that's what I have for today, everyone. Thank you very much for your time, and hope you enjoyed the webinar. Let me know if you have any questions. BENKEISER@aft.com. Have a wonderful day, and we'll see you all in the next webinar.